Welcome to the Cosmic Pie Podcast, episode number 41. I'm your host, Wayne Barkhouse, and here with me, as always, is
Robert Moore. Nice to see everybody.
I've said that like 41 times now, you know that?
Yeah, like 41 times. Yeah, I think it's been 41
Well,
times.
actually, less than that because I wasn't here every single podcast.
True.
So I did miss a couple of them, right?
Yeah.
Now, today, Robert, we do have a special guest.
Mm-hmm.
Parker Johnson is joining us.
Hello. Thank you guys for having me.
So Parker, for those who don't know, which is probably most people are watching this, but not everybody, Parker is a physics major in the Department of Physics and Astrophysics here at the University of North Dakota, and that's where we're broadcasting live from on campus here in Grand Forks. By the way, if you have any questions or comments throughout the podcast, please feel free to use our chat option. That's up and running now, and you can see a couple comments there already. Thank you for those who comment. Now, today, as I mentioned, Parker is joining us to talk about research that he's doing as an undergraduate student. So I think, Robert, we should turn it over to Parker and
I think we can.
see what he's into these days.
Go into his work.
Okay, Parker, take it away.
All right. Yeah. So a quick introduction to myself. I'm Parker Johnson. I'm a senior physics major, and then I'm also minoring in computer science and mathematics. So I've been doing research with the observatory here at UND for about 2.5 years now. So we'll be talking a little bit about my exoplanet work, and then also what I did last summer, working on simulations at Stony Brook University in New York.
Okay, so first of all, Parker, what I did last summer, Robert, that opens
I
up.
wasn't going to say that, but yeah.
I had to, sorry. That opens up some interesting things we could talk about, but we won't go there. Okay?
Right. So,
But Parker, you mentioned exoplanets. So first of all, I'll let you describe in detail what an exoplanet is for those who don't know. But, arguably, the discovery of exoplanets is probably the most exciting thing in terms of capturing people's imagination. And I mean here, not just the scientific community, but the general public.
right.
In the last nearly 30 years now, so it was roughly in the mid-90s when the first exoplanet was detected. And so I think the reason for that, and it'll become obvious when Parker presents and discusses this topic with us, is that it makes it open your wonderment of what the heck are on these planets.
Right.
You think of our own solar system, and people wondered for many years, what's it like on the surface of Venus? We see this bright object in the sky most of the time, either just after the sun sets or just before the sun rises. Is it like an Earth? I mean, can I roam around the surface of Venus?
And in fact, there was plenty of science fiction short stories that were made about people living on Venus.
Well, what's Venus named after?
Right, the goddess of love.
The goddess of love. So who wouldn't want to go there at least once
Right.
in your lifetime?
And,
Well, and then think about Mars.
and with those thick clouds, it's probably a steamy jungle there,
Well, what about Mars?
right?
How often have we written and talked about Mars and movies and, you name
Yeah.
it. So exoplanets, planets in general, have captured our attention, over the years, and hundreds of years, not just the last 30 years. So Parker, what do you mean by exoplanet? Can you maybe first define that to people?
Yeah. So for those who may not know or aren't familiar, an exoplanet is any planet outside of our solar system. So we're not talking about Mars, Jupiter, Venus, any of those planets. Anything orbiting a star that is not our sun is a quick definition of an exoplanet.
Okay, so and when you think about an exoplanet, right away, like I said, it captures people's imagination. The reason for it is, imagine a planet going around some other star that's not only in our own sun. What the heck is on that planet? Is it like dinosaur creatures on that planet? You'd wonder, right?
You do.
Is it some advanced intelligence? I mean, and then maybe they can share our secrets to how that we can live longer, or maybe solve the climate and energy crisis and all these other things that would be examples of questions you want to ask.
Or maybe they're going through the same type of crises themselves.
Maybe. Or maybe, and hopefully not, maybe they are hostile. And maybe you're trying to contact the Borg, for those fans of Star Trek.
Here's hoping not.
Yeah, and they will
And that's what
simulate
we're
us.
trying to figure out.
Yep.
Yeah, maybe they want to simulate us, right? If we give away where we are, this kind of thing. So Parker, why has it taken, up until roughly 30 years ago for us to even determine that there were other planets orbiting other stars?
Yeah. So, I mean, detecting them is very challenging. I mean, you even look at our own solar system, it's tough to detect those planets sometimes. So really the technological advances that have came with the new instruments and telescopes have pushed their discoveries of exoplanets. which we'll talk about a few of the different methods on how you detect them later today.
Okay.
Right, so that's just another example. You could say, that ever since the time of Galileo, when you think about, the invention of the telescope just before Galileo used it, and Galileo didn't invent a telescope. So who invented the telescope, Robert? Do you remember?
Hans Lippershey is who I've always heard.
Yeah, that's the person who's got credit for it.
Yeah, the Arabs actually had it, and possibly the Chinese had telescopes before those guys did. But
So-
in Europe, it's Hans Lippershey usually given the credit.
Right, and so what Galileo did that others didn't do before him is he looked at the night sky, wrote down a description, your drawings and so on, and then published what he observed. And that's
Right.
the key point, publish. In fact, that's how all modern science is done in terms of the advancement of knowledge, is by publishing so that others can see it. And of course, we have peer review process in science and so on to make sure that you're not just publishing things that are not
Just
truth.
not making stuff up and
Yeah,
saying,
exactly.
here you go.
And even that happens occasionally.
It does
and
happen,
unfortunately,
yes.
there are
Unfortunately.
yeah, you get in trouble for doing that, as you should. Now,
And correct me if I'm wrong,
Yeah.
but I believe the first exoplanet was theorized in the 1920s, around there.
well, you could go back to Bruno days,
Right,
Yeah.
right? Who was burned at the stake for a lot of his views. Most of it was anti-church,
Right.
right? And Bruno was burned at the stake for his ideas that there were essentially an infinite number of planets out there, worlds that were like our planet. Like, in other words, it would have life.
Right.
And so there'd be an infinite number of places, locations out there in the universe in which life would be at. Supposedly the church didn't burn him for that thought. He said a lot of other stuff that were direct
I
connections.
was
to the
about to
running
say,
of the
yeah,
church.
he said a lot of other things
Yeah.
too.
So anyways,
Yeah.
that was like early 1600s, like
Yeah,
1600 or something like that.
I like pointing out because people go, Galileo had it in for the church. And it's like, no, he grew up with the Pope. They were childhood friends. That's why he wasn't burned at the stake.
Right.
He was given house arrest instead of being tied to a pole and said, here, you're on fire.
But yeah, since the time of Galileo, because of the advancement of technology, that really has the major impact on our advancement of knowledge
Yes.
in astronomy and astrophysics. And this is another example of that. As Parker mentioned, it's the advancement of equipment, instrumentation that allow us eventually to be able to detect exoplanets.
Right.
I mean, that's much of science, though, is it gets theorized and then it takes sometimes decades for the engineering and the technology to catch up to the point where you can actually detect something.
Right.
Yeah. We got the thing in science, at least in astronomy, the Copernican principle after Nicholas Copernicus.
Mm-hmm.
And essentially what it means is there's nothing special about your situation.
Oh, okay. Yeah.
So it's not like you are on a planet that goes around a star and it's the only star in the whole universe out of literally trillions and trillions and trillions and so on of stars out there. None of the other ones have planets, only your star.
Right.
That's that. Like there's something special that we're at the center of everything. They're all. So ever since Copernicus and the 1500s, we've been going away from that idea. So anytime if you think of something or propose an idea which places at a very special situation, you always think of Copernicus and said, maybe I'm not looking at it the right way.
Right.
And so the idea that there would not be planets going around other stars seems kind of weird because, based on the Copernican principle, yeah, there's probably planets going around a lot of stars.
Right.
And what it really boils down to from the point of view of the public and the imagination is there life around any of those planets? And that's a different question altogether.
And that's something we're still trying to get the technology up to a level where we can detect.
And then we've talked in the past, too, about the James Webb Space Telescope and
Yep.
its ability to essentially taste the atmosphere of some of these exoplanets, looking for signatures of life, technological signatures. Right? And so that's some of the things that we can do is we can look at planets and then go even further and say, is there any evidence that we can gather with what we have today that points towards the fact there may be life on those planets? But Parker, you mentioned that the detection of planets is that's the first step, right? Are there
Right.
planets? And then we can
Right.
go on after that. So can you maybe outline, show us some of your work of what you've done in this whole area of the detection of these exoplanets?
Yeah, let me share a PowerPoint for you.
And I'll pop him up on full view.
Alrighty, can you see that?
Yeah, I can see it. There we go. Now I'm seeing it as a presentation. So yeah,
Okay. Yeah. So, I mean, like I mentioned before, one of the projects I've worked on at UND is a survey for those exoplanets and analyzing their light curves.
Okay, before you move on, let's make it clear because some people may not get it. The first slide that you show there is a planet. Which planet is that?
Sure. Yes, that is technically Earth for that illustration.
Okay, so a lot of times, and this gets to a point we talked about miscommunication in science, that when somebody will, an artist, will make some kind of nice drawing of a planet.
Yes.
And they'll talk about exoplanet A is this properties that we can determine. And then people think that because we had this beautiful picture, not too unlike what Parker's showing here, that actually is somehow an image that we've taken of that exoplanet.
Yeah.
And in fact, of any planet beyond our solar system, we have not resolved those planets. We see there are a few of them, and that's a minority that we see as points of light orbiting the host star.
Yep.
They are completely unresolved. We do not have pictures of them like you see here.
I will point out that even the ones that we have direct images of, that's a heavily processed image where the light of the star has been removed to see it. Because otherwise, think about looking at the surface of a lake, how much it glares. That's what happens with a star. So you've got to remove that starlight, that glare, to even see the planet.
Do you realize a few years back, I don't remember exactly when it happened, but it was quite a while ago now, that NASA was actually criticized for the release of color-enhanced images of like Jupiter and the Saturnian system and so on, because people thought that that's exactly what it would look like if I were there looking at the planet with my own two eyes type of thing.
Right. And it led to a lot of people saying, oh, it's just cartoons. And it's like, no, if you could see in these wavelengths, that's what it would look like.
Yeah, so you have to watch it when you're, doing science communication to not take down the public down a road you don't want to go, right? To make sure everything's clear up front.
Right.
So, yeah, that is a great point that this is not how we detect them. We don't take clear images. It's a lot of analyzing data.
Yes.
Okay. Yeah, so go ahead, Parker.
Yeah. So the first thing that we can discuss is the different methods. So right now, leading by far is the transit method, which is what I've personally used with my work. So what that is, as you can see on that image on the right, a planet will transverse the disk of its host star, causing the light to dip down. So what we're detecting are the photons from a star, or the light, and when that decreases, that indicates a potential planet.
Okay.
Right, so those percentages that you see there, like 75.6 and so on, that's the percent of exoplanets that have been detected to this date by those particular methods. Is that correct?
Yes, and I mean that's changing all the time.
Right.
I believe this image is from last year, so those numbers could be a little different.
But it gives us a general idea. The vast majority is through this transit technique.
Right, for sure.
Okay.
And then the radial velocity method is another popular method that I believe Dr. Angel Tanner, is that her name, who was on here a few weeks ago? That's how she uses that method, which is when a planet gravitationally affects its host star, and you can measure how the host star is moving. Some other methods that have been used are gravitational microlensing, which is when in the Earth, a star with a planet and another further star align perfectly and causes an enhancement of light that can be detected as the planets. If you guys have anything else on that, please jump in.
Right, so this gets back to essentially general relativity, ties in directly with that. That the presence of mass or energy, and you can think of in this case of being equivalent to E equals mc squared, the most famous equation in all of physics, arguably, that the presence of matter / energy causes space-time to be altered or distorted or curved, as we would say. And it's from the curvature of space into the vicinity of a star, right, and a planet, so any object that has a mass, for example, will curve, that the light will not travel in a straight line. That only occurs in flat space, what we call Euclidean space. The geometry that you probably learned in high school, Euclid geometry and all the postulates and axioms and all those wonderful things. Two parallel lines remain parallel forever. But that's all assumed that it was flat space.
Right.
Anytime space is curved, then that's not necessarily those theorems are true. And most of them are not, as far as I know. And so you can get this enhancement of the light. because of the alignment of the planet with the host star. In fact, it's almost like a lens, using a lens to look at a light source where you can zoom in or magnify some faint light source using a lens, and the light from that faint source is passing, it gets bent or refracted, passing through the lens.
Right.
In this case, it's the mass itself that's causing the curvature of space and time, not a lens actually doing
Right.
Right.
So, yeah. And basically, we can tell the mass of the object because of how much it brightens the star that's behind it. You can determine how much mass has to be in the way, and if it's not stellar mass, and it's much smaller than that, it's probably a planet.
Right. So the limit there is about 8% of the sun's mass. That's the minimum amount of mass a star can have, so that it has sustained hydrogen fusion into helium in its core.
Right.
So if you have a mass less than that, a little bit less, we call those objects
Brown dwarfs.
failed stars.
Failed stars, right.
But it's just a continuous range of masses. So if you go down to lower and lower masses, you're into what we really call planet size scale.
Yep.
In fact, you can continue down that slope and get into asteroid and comet size, down to boulder size, pebbles, and eventually into dust grains.
Right.
So there's a whole continuum of sizes and masses.
Dust grains we spot because they they absorb light and then re-radiate it as infrared. So there's what we call an infrared excess. So yes, folks, we can detect when there's a dust cloud. So
Something I want to bounce off of, Rob. You mentioned that from microlensing, we can actually get the mass. So that is one of the downfalls of this transit method is, yes, it is very efficient at detecting planets, but it does have some limitations. And one of those being it can't detect the mass.
right, you need radial velocity and transit.
Correct.
To
Yes.
get the
But
mass.
Once you detect it with the transit, you can bounce to another method like the radial velocity to get the mass.
Yep.
But can't you get information about the relative size difference?
Yes.
Yes, you can get the radius.
Right. So that will give you some, if you assume a certain density, of course, which
Right.
is a big assumption, then you can get a mass
Right.
range out of
That's
that.
a big
right?
assumption, though.
Well, you look at what we know,
Yeah.
right?
I won't disagree.
And you look at the most massive, most dense planet and the least dense planet, and then you've got a range of masses you can play with.
Yep.
And the transit method also has a bias towards what are called hot Jupiters. So these are Jupiter-sized planets or bigger that are orbiting really close to the star, like closer than Mercury is to our sun.
Right.
So, I mean, for obvious reasons, if it's closer and it's bigger, it's going to be easier to detect using that method because it's blocking more of the starlight.
Right.
Right.
And in fact, that bias of being closer and easier to detect, that also affects radial velocity detection method as well.
Right.
And
Because the gravitational interaction is dependent on that radius or the distance between the planet and star.
Right. So the closer it is, then the more tug you're going to see. You'll be able to
Right.
detect from here, whether it's a blue shift or a red shift, and combination of them when it's going around, of course, right? Depending on the exact placement of these objects in their orbits relative to each other.
now,
Yeah, so we're trying to find more rocky planets like Earth, but that seems challenging because of that bias towards larger gas giants.
right.
Right. So it's not unusual. Maybe you'll get into this a little bit. That if you did the first, I don't know, probably 100 exoplanets that were detected, by far they are dominated by the ones you mentioned, Parker, the things that are Jupiter-sized or larger, and also very close to the host star.
Correct. And that's why it's such an exciting time right now with James Webb just coming out, because now we're being able to see further and dimmer stars to see these smaller planets.
Yep. Now, I'm going to mention one thing. You left off one method of planet detection, but it does have so few planets that are detected this way, and that's the astrometric, where we actually analyze the full motion, not just the radial motion of the star. And but you can probably count them on both hands, the number of planets that have been found that way. So,
Right. I think the direct imaging is something that might take off with new technological advances to actually get physical pixels lit up of a planet. They're not going to be as resolved as that first slide that I showed, but to actually see a pixel of a planet will be exciting.
Oh, yes.
Yeah, and to get to the point where we put up our space telescopes and make them large so that their diffraction limit, that's what they would be working at essentially in space, means that we can take very high resolution images of these exoplanets, at least hopefully some of them that are really nearby that we discover. And that with a large enough space telescope, we might be able to get multiple pixels for one exoplanet. In fact, you can imagine that at some point, you can start to see maybe atmospheric features on the planet, or even surface features.
Yep.
Gross, large scale type of structure in the beginning. But as technology improves going forward in the future, I mean, this is only going to get better and better and better, right? So.
Yep. Got 2 words for you. Space interferometer.
I got 3 words for you.
Yeah.
Born too early.
Yeah, I know. Yeah. Yeah. But that's what we really need is a space interferometer.
Yeah, and then, things like we talked about even last podcast about Starship and how important missions like that are to the advancement of things like, space-based telescopes, because the cheaper it is to put these things in space, the more things are going to happen.
Yes.
Yeah, it'd be wonderful to do all this, but you got to come up with the money somehow or make it cheaper.
Yeah.
So, Parker, get a good job when you're done here at UND.
Yeah.
And don't forget about us.
I know. Yeah. Anyway.
Yeah.
And then that last method, pulsar timing, I believe the first exoplanet detected was using that method. Is that correct?
Yes.
Yeah, that's right. That's
Yes-ish.
Right.
Yeah, planets around a neutron star.
Yeah.
Which was really bizarre.
And naysayed for about a decade before they finally went back and go, okay, yeah, you were right.
Well, the thing is, you'd never expect planets to survive, to be around a neutron star, because a neutron star is the end result of the core collapse of a massive star that went supernova, that basically blew up. And the idea was, if there were any planets orbiting that star before it went supernova, they have surely have been destroyed afterwards in the supernova explosion.
Right.
And yet, the first planets that we find are going around a neutron star.
Pulsar.
So the idea is, while those planets around that neutron star, maybe they coalesced the material and formed after the supernova. So the leftover debris. Maybe there were planets going around the star before it exploded, and these new planets then have been formed from that debris. Mm-hmm. We just don't know. But that result was a complete shock to everyone. That's why it took a while for everybody to accept it.
Oh, yeah. Yeah.
And I think the first planet that was observed going around an ordinary star, not a neutron star, was 51 Pegasi, if I remember correctly.
Yep.
And I think the people won the Nobel Prize in Physics for that discovery just a couple of years ago.
I'd have to go back and check.
Yeah.
Yeah.
I'm almost certain of that. And so that's when people kind of relate that discovery to the start of all this. But no, it was the first exoplanets around a neutron star that was the first one that were verified.
It's just, other planets around normal stars had to be found before people went back and looked at their data and said, they were right. These are planets around a pulsar.
Well, it's interesting to note that we know of literally thousands and thousands of pulsars, which are most easily found through radio observations, pulses of radio light. And people have looked for other planets around other pulsars, neutron stars.
Right.
And I think they only found one other example of it. It's a very low number. So in the vast majority of cases, when a core collapse supernova goes off, chances are the host star probably had planets, because maybe, Parker, you'll get into this a little later. Statistically, we think that there's roughly at least one planet orbiting every star.
Right.
So from that point of view of just statistics alone, there probably were planets going around some of these progenitors that created these pulsars. Yet where are they? So whatever formed these planets that we have detected going around neutron stars, if they formed after the supernova event itself, that process, whatever it is in detail, is fairly rare.
Is rare.
Because we only see it in a couple cases out of literally thousands of examples.
Right. So, yeah.
But your imaging number there is 1.2%. So that means direct imaging of exoplanets is of the order of 1 out of every 100. Is that what you're saying?
Right. As of right now, yes.
Okay. That just tells us that we have to improve our technology to be able to image, directly the planets going around.
I would bet that a lot of that has come about recently with James Webb, to be honest.
Yeah. Well, that's one way. I mean, the problem in doing that, and as you alluded to already, Robert, is it's like trying to find a firefly that's perched on the edge of a searchlight.
There you go. That is a very good analogy. Yeah.
And the way to do that is to somehow, if you can, artificially block the light coming from the searchlight, allowing you to see the much fainter light of the firefly. And one way to do that is to go to other wavelengths other than optical.
Right. Infrared comes to mind.
Infrared comes to mind. But then you have a problem once you look at longer wavelength. The diffraction limit then is greater, which means poor resolution. So
Right.
you're always fighting against longer wavelength and then having enough resolving ability to see these objects.
Right.
And so that's the trade-off.
The point though is, and maybe we should do a show like on this, the point is that the star is about 1,000,000 times brighter than any planet in the optical wavelengths. But when you get out to the infrared wavelengths, it's just a few tens of thousand times brighter. So
Right. So that's what they look at. And then they put what's called a coronagraph over the star, which blocks all of its emissions or part of its emissions. And then you can see the thermal emissions from that planet.
there you go.
Yeah, exactly.
Yeah.
Right.
So, there's a lot of work that goes into getting those direct images, and even then they're a dot.
Right. It's a single pixel.
Right. So, yeah.
Okay, well, I got some transits from my work at our observatory at Martin's Observatory, about an hour north of Grand Forks. So this is Trace 1B, and this was actually one of the best transits that I've gotten.
Yeah, that's a good transit. That's a good detection.
This is about as good as you can get with the 20-inch telescope that we have.
And it's indicative of a planet because it has that flat bottom. Because stars are going to be about the same size, so an eclipsing binary makes a U shape, round bottom curve, whereas this one is flat, so something moved in front of the star, was there blocking light and the same amount of light for a while, and then went away.
Okay, Parker,
So
you have to explain, of course, what's being shown here to somebody who's not familiar with this type of plot.
Sure. So on our x-axis, you see seconds. So this is over the course of 5-6 hours. And we have about an hour before the transit starts. So before the exoplanet gets in front of the star. That is why the normalized flux right there is at a 1, standard 1.
Can you explain what flux is?
Yeah, so that is what we measure. We measure the intensity. So the flux is more or less the intensity of the starlight that we are observing with our telescope.
So
it's how bright the star appears to be in the sky.
Right.
Apparent brightness.
Yes.
Okay.
So then you can see it as it transverses the disk, it starts to dip down. And then when it's fully in the center of the star for that period of 2 hours or so, however long this is, it's a flat bottom and then it leaves the other side. So that is what you're seeing here. And then another thing worth mentioning is that blue line is not the best fit. It is actually a model that I implemented in Python, taking into account the normalized radius of the planet, the radius of the host star, was something called the impact parameter, which is where the planet is orbiting the star relative to the center of the star, so that distance. And then it also takes into account the predicted transit time and a few other things.
So just to interpret this then, when you look at the plot, the way to look at it is to start from the left side.
Right.
So if you see the 0 at the bottom axis, the horizontal axis, then you go up, and the normalized flux is at 1.00. In other words, the star is of a certain brightness. We'll call that a brightness of 1, just to make things simple. And when the planet starts covering the star ever so slightly and more until it's got its maximum coverage that the planet can do, that light goes down until it reaches the minimum. That's at a little bit above, looks like 97% of the total brightness. So the brightness has dropped by a little over 2%, 2.5% roughly.
Yep.
And then on the flat part, where the blue curve, the model, shows it's a horizontal line sort of in the middle of the figure. That just means that the whole of the planet is covering the star at some part, not necessarily in the center of the star, but somewhere in the field of view of the star itself. Right. And over time, that planet then will appear to move across the surface of that star. And so the light will not change because all of the planet is blocking out a fixed amount of light. So that's why you have this fixed level at about 97.5% or so. And then when the planet starts emerging outside of the star, the light level will come up because less and less of the planet will be covering the star itself until eventually all of the planet has moved away from the star from the point of view of us, and the star is back up to the brightness it had before the planet started covering the star's surface. And that's what you see on the far right when the line goes back up to a 1 for normalized flux. Is that how it works?
Right. That was a great explanation. Yep. So this is what the transit method actually looks like with the data, and this indicates the detection of a planet.
Yep. And I can tell certain things just by looking at it. It's a giant planet. It's a gas giant planet because it drops the light by 2.5%, which is a significant amount. So it's a large planet. You can tell that it went across the full face. The full planet was across the disk because of that flat bottom and just various things like that. And this was a good light curve. This was a good night.
Yes. Now, from just this light curve, we can get things like the radius of the planet. We can get the semi-major axis from Kepler's laws. Mm-hmm. Everything that we are interested in besides the mass, which is important, but we could also infer it from its volume.
Right.
Now, Parker, one of the things, of course, in science is that every measurement that you do has an associated uncertainty.
I wasn't going to say anything. I know where this is going.
And so,
so do I.
Right. And so the uncertainty in this case, the true dispersion or the spread in the observation is one way of measuring that uncertainty. And so you see that the data points, those circles, are not making a perfect line or a curve, that they're scattered about. So that gives you a measurement of the uncertainty. And so one of the things we look for is the uncertainty in your observations small enough that that decline of roughly 2.5% in brightness is a real effect and not maybe statistically it was just a fluctuation to the low side of things and it masks as a fake exoplanet, if you like. But, based on the scattering that I see on the plot, that dip in brightness is definitely several times that scatter. So this is a real dip in brightness, not just some type of uncertainty in the observations.
And I thought you were going somewhere else with this, with that line of questioning, because a friend of mine, I started posting light curves that I'd done, and this friend of mine looked at them and commented, error bars or it didn't happen. And error bars are, again, a measure of that uncertainty, and you can should put them on each of the dots, each of the points, and that would give you how uncertain these measurements are.
Yeah, and if you get into the nitty-gritty, though, you have like individual uncertainties of measurements.
On each error bar.
But then you have statistical uncertainties as well. So there's statistical and random uncertainties. And when you combine all of that, that's what gives you that scattering that you see in the data points. Because someone might wonder, why aren't those dots all lined up in a nice bottom? Like, just focus on the middle of the plot where the line is horizontal. Why don't all the observations go along that blue line? For example, I know you said it's a model, but why are all the observations not making a line somewhere around that general vicinity? And that's because of the statistical and the systematic uncertainties on everything combined gives you that spread that you see there. But the spread itself gives you a good idea of what is the uncertainties overall in your measurements. And based on what you see in this plot here, that dip is way greater than those uncertainties. In fact, by several. I don't know if you actually calculated, Parker, what is the RMS of those data points and how does that compare to the dip that you see there of a 2.5%? How many sigma would that dip be or correspond to?
Right. I have not calculated that, but that is something I should do.
Yeah. And I mean, but just by eyeball, it looks like at least 5 to me, if not more.
Yeah, that
Yeah.
seems a good call. Yeah.
Yeah, and
This
so
is an excellent detection.
that would be
This is
definitely a
beautiful.
detection, right? Any
Right.
science, usually, the 5 sigma detection is what you aim for if you can get it, and that's clearly what you're seeing here.
Yep. Beautiful detection. So
Yeah, so now we'll go into not so beautiful. I mean, these are still good transits, but there's some physical things that cause this spread just with being a ground-based telescope. So one of them is if you have a full moon out, you're going to be detecting some of that light, which is going to cause more scatter. If it's lower on the horizon and you have to go through more of the atmosphere and you see the stars twinkling, which is not good if you're an astronomer, that means the light's scattering on its way down towards you. I mean, on this one, you can see it either went into, it could have been going into the sunrise and the sun started coming up. Other certain things can happen like that. So this shows a little bit more scatter.
So I missed what the label was on the first one. Is this the same one or a different one? In terms,
That is
that's
trace
1B. Okay.
And this is trace 3B. And then the next slide is also trace 3B.
Okay. Now, do you want to explain first of all what trace comes from? What does that mean?
Yeah, so I mean, it's the naming of exoplanets. So let's say the Kepler telescope discovered an exoplanet. It would be named Kepler and then some number. And then B stands for it is the first planet in that solar system, so to say.
yeah.
Right. So TRESS is named after the NASA space telescope that's in space now, making observations, looking for the signs of exoplanets.
Yeah. I will make a note too that it's a planet is designated by a lowercase letter B. If it were a companion star, it would be an uppercase B.
Right.
So that's an important thing to note too. And yeah.
So this the TRESS mission then is publishing all of these target lists of interesting objects that appear, like stars appear to have exoplanets. And what astronomers are doing is then going and looking at these targets, doing follow-up observations.
Correct.
So that means you knew these objects, the 2 that you've shown here, were in
Right.
this catalog. You're not like you're picking a random star, and people shouldn't think this, that somehow you picked a random star and observed it and found these exoplanets, that this was suspicious of having exoplanets. It was measured already by NASA. It's just that the nitty-gritty details aren't measured, and you need to do this more detailed follow-up observations. Is that true?
Yeah, so that is an important point. So we are currently not in the business of discovering new exoplanets. We're in the business of following up potential exoplanets. So from these big space missions like Kepler, like TESS, all of those big telescopes in space, they'll be surveying much of the sky. And when they have a potential candidate, it gets followed up by ground-based telescopes.
Yeah. You've got to have 2 follow-up observations for it to
Right.
count as a detection.
So-
And another important thing is for follow-up transits, you can actually get the period, how often it's going around its host star, if you continuously observe that star every night.
So, and the other thing is too, what filters did you use to make these observations? I know it's in the optical, but is there a
Right, so
particular
this is
filter?
all in the V filter.
Okay. So on the blue side, we call that the B filter, B for blue, you could use. The red side would be an R filter, R for red. And then somewhere roughly in the middle would be the V filter for the
V
visual filter, as we would say.
Yep.
Yes.
So it's roughly in the middle of the optical spectrum.
And for
So-
our audience that is in the know about things, this is the Johnson and Cousins filter set, right? Yeah. So anyway, you were
Yeah, no, you're fine. I was just going to mention why we chose the V filter, and that is because those other filters, like Wayne mentioned, the U, the B, the I, all of those filters, we're interested in the amount of photons we can detect, which V gives us the highest amount of photons. If we're only interested in the dip, that's when you want the highest photons.
So why can't you observe it with no filter?
You could do that as well.
Because that would then give you the maximum number
Maximum.
of photons.
and
Right.
I know the answer to this one too, but go ahead, Parker.
I believe on our telescope, we don't have a slot on our filter wheel. that has no filter on it. So we have to choose one of them.
Okay, so that would be a thing where you'd want to have that maybe.
Right.
Right. It's not ideal, but we
If you-
use the one that we can get the most from.
Right.
Yeah. I think it's a matter of the number of positions on the wheel. It was either have an open slot and not have one of the other filters, or have all the filters and have no open slot.
Now, for this particular light curve, as you say, you picked one that looks ratty, if you can use that description, compared to your first one. And notice coming out of the eclipse, right, the data points fall well below the line. So as if you get this decrease in brightness. So are you thinking that's because of the sun? Dawn is approaching?
So for this one, I think that was because dawn was approaching. You can see the normalized flux is going linearly upwards, which
Right.
shouldn't happen. For this one, I think the star dropped lower in the atmosphere, so we were detecting less of its light because it had to go through more of the atmosphere to get to us, so some of the light would scatter, and we weren't detecting all of it.
Yeah, because this part of the process, I assume, in doing your brightness measurements, is you look at the brightness of the sky in the vicinity of your targeted object.
Right.
So that brightness will change, depending on whether you're heading into dawn or just in dusk still.
Right.
But
Right.
supposedly, because you're making that measurement directly of the background sky itself, that's not going to affect your observation,
It shouldn't, but it does.
right? But that's the kind of thing you're looking at, right? So you'd have
Right.
to. It's not just a simple matter of the moon was near my object or not, because you are sampling the background sky around your
Right.
object, which would include the effect of the moon, for example, the scattered light from the moon.
Right.
So it's more complicated than that. That's kind of what
Yes.
I'm getting at.
Oh, okay. Yes. Yeah.
Oh, yeah. I was just trying to list some physical problems with observing from ground.
Right.
I mean, quite possibly, well, with the length of time, but you can have transient clouds pass through, and you'll see the effect of that in your
Right.
flux.
Right. If it's not a fully clear night, and I think this, I can't see because of the zoom bar, but I think this one was in June when it was taken.
May.
May.
Oh, okay, May, yeah.
This is May.
Uh,
But I mean, the other thing is, you're just looking at relative difference in the flux, right?
Right.
The change. So you don't need to calibrate it to anything.
Right.
So as long as you do the proper background subtraction of the light around the star, you should be fine, whether or not it's in a cloud or not.
Again, should,
To first order effects.
but it happens.
Yeah.
And this is one of the reasons you also there's a planet database, exoplanet transit database out there that they're literally getting hundreds of observers around the world to send in their data like this, and it's so that you can overlay it and get a more detailed and better sigma on this, because you've got more data, and hopefully more quality data.
Well, that's not unlike the AAVSO people, right?
That is very similar to what AAVSO.
The variable stars.
Yeah, American Association of Variable Star Observers. For
Yeah.
those that don't know what AAVSO means.
Right. So they do the same sort of thing. But even the scattering amongst like the first one you showed, very first light curve, that scattering, to understand that is also interesting. Like, where does that ultimately come from? Why aren't all your data points lined up, and why do they have this scatter?
Yeah.
Right.
And you're right. You're comparing to another star in the field, and the field of view is very small. So you'd think that there'd be no cloud or other factor that would go across it, and any sunlight rising would affect both. But it doesn't. There are those slight differences, and they show up. And the shape of the mirror can cause effects.
So Parker, this is not like a phased diagram, right? These are just observations taken on, like you have labeled there, on one particular evening.
Yes, correct.
Yeah, because you could combine observations taken over multiple nights and make a phase diagram.
Yes.
Which that's something I could do with these transits, because I got multiple observations of trace 3, which is seen right here.
So in other words, a phase diagram, for those who don't know, if you go back to your first one, your good one that you showed, the best one, this one here, you can estimate where the exoplanet is starting to cover the star and where it exits, on the other side. And then you can line up your light curves taken on different nights so that they lined up exactly in the same way, so that you have where they're first entering the star, the exoplanet, is all lined up, all your observations, and stack them together that way. And that's what we call, lining them relative to the phase of the system itself.
Yep.
And that
So that's a benefit of getting multiple transits. So that's something we could do with these.
Right, and that would clean up a lot of that scatter.
Right.
Because you have more data points, basically.
And that's what I was talking about. The Exoplanet Transit Database, ETD, is trying to do is get multiple observers, combining all their, making changes, shifting due to the different equipment and so forth, and saying, here, we're getting solid light curves instead of spotty light curves.
It would be like, for example, if you wanted to measure the length of a table, and you do it once with your tape measure and write that number down, and then you do it again, let's say an hour later, independently, as much as possible, and then you might have, 10 different times you've done it over the course of several days, and you won't get exactly the same length because of the positioning where your eye is looking at the tape measure and so on and so forth, slightly different angles. And so you'll get a scatter of observation, of measurements in this case. But then if you get multiple people to do that over the course of a year, so let's say it's a class project to do something like that, then you might have, 1,000 observations. And if they all cluster in one particular number, then chances are there's a high probability that that's the length of the table to very good uncertainty, right?
And
high
that's
precision.
exactly what we try to do.
Yeah.
Right. Yeah, so I got one more transit to really show the scatter. So, you can still see the dip in the transit, but this is a very dim star. This is one of the dimmest stars that we observed with a transiting exoplanet. So you can see the variation in data points for sure right there.
Well, what about the model for this? Now, where does that model come from? What's input into this model?
Yeah, so the input is the normalized radius of the planet. So that takes into account the radius of the planet and the radius of the star, and then normalizing that. And then it takes into account the impact parameter, which, like I mentioned before, is where it's orbiting around the star. So if it's orbiting on the lower side, it's going to have a higher impact parameter than if it's orbiting straight through the center.
Right. So just so people are clear on this, so if you envision a single planet going around a star, and you define that the orbital motion is in a plane, then that plane, like looking at a piece of paper edge on, can be tilted towards you or away from you. And that means that the planet, as viewed from us, would not go necessarily make a cut right through the heart and center of the star, but would pass up top more or maybe down below, right?
Or on a diagonal.
Or even at an angle, right? If depending on all the alignment. So that's what you're talking about here.
And that's why we can't even detect the majority of transiting planets, because they don't transit around that disk. Because if you're off by plus or minus 5 degrees of inclination, you're not going to be able to see it, because it's not going to block this light.
Right. So from our point of view, right now, right, we wouldn't be able to see it. But that makes me wonder. Could you actually model, if you look at some star and figure, hey, I can barely observe this transit, just cutting across near the polar region of one of the stars relative to us. If I wait 20 years, because of the orbital motion of both our sun and the star, that it puts me in a better point of view of seeing a much deeper transit.
Right. Or it might put you in worse.
I wonder if that's ever been done.
Don't know. That's an interesting question, though.
And with Gaia, right, you have, that's our best measurement we have of motion of stars, right, around our Milky Way. So I wonder if you could do that, if you could make that type of prediction. That would be interesting.
But I was going to point out that the shape of that curve, that blue curve, the shape of the transit, as we'd say, can tell you that impact parameter, how it's going across the disk of the star.
Right. So for this one, you see that it's not a discrete flat bottom, as opposed to this one is more discrete. So this planet is orbiting more through the center of the star, whereas this one might just be scraping that bottom. side of the star.
But you still get a distinct flat bottom compared to what you would with a star going in front of a star.
Right.
Yeah, because notice, on the bottom there, you're still talking about a 2% roughly dip in the brightness of the host star.
Yep.
Mm-hmm.
So that's pretty significant still. But the observations are a lot more scattered, than what
Right.
you had previously. So yeah, redoing these observations, because this is a single night in June now, this June 2nd of last year, then redoing these observations may be a way of reducing that scatter and then be able to tell for sure if this is a significant detection or not.
Because I got to admit, on the basis of this data set alone, I don't know that I'd call that a detection. But
yeah, for sure.
Well, let's put it this way. I could draw a straight line through there
Right.
and not show a dip at all. And argue that statistically it was a valid fit to the data.
Curve, or a valid
Probably
fit.
do a linear fit with this. Yes.
Yeah.
But
So-
that's how science works, right?
That's how science works. Yeah.
You do this sort of thing, and this may tell you, though, when the eclipses are taking place, right?
Because I can definitely see, I'll agree, there is a decrease in the amount of flux, the amount of light that's reaching us. Is it a planet, or is it a white dwarf companion or something like that, though? That remains to be seen.
Yeah, and the more information you got about when these dips take place, in other words, more information about when the exoplanet actually transits in front of the host star can then set you up for further observations. You're
Right.
prepared to look at those times rather than spending a lot of time waiting around for it to occur and it never occurs. So
Right.
from the efficiency aspect, right? It's
Yep.
nice to know exactly, roughly at least, when, is it between 2 a.m. tonight and 4 a.m.? Or is it between, I don't know, 7 a.m. and 6 a.m. going right around the clock,
Right.
In other words, you don't know, right? There's no constraint there at all. So
Right.
So, yeah.
Well, I do have another topic to discuss, and we have limited time. So if we want to jump to that.
well, unless you want to wait and we could do another podcast,
we
Parker.
could get you back
Yeah.
on. Yeah.
Yeah, so we
Yeah, we can do that too.
Yeah.
kind of stick with it. So well, one thing I would ask anybody who does science, of course, are you planning to publish your data? So do you have any words you'd like to share with us, maybe on follow-up of these objects, what you plan to do, or maybe in publishing or whatever?
And
Yeah, so I'm planning to publish or get more follow-up transits of planets that I've already imaged, and then publish more or less a survey of all the follow-ups that I've taken.
we do have a couple of questions, so I'm going to throw that in there.
Okay.
From Mizuho Swam. Back to the basics at some point, would you explain again why the flux is lower around 5,000 seconds? And B, why it's symmetric with 5,000 second line? So I'm not seeing the symmetry issue, but
So he's saying, why is the flux dip at that 5,000 second line?
yes.
Yes. So when we're imaging these exoplanets, we try to get at least an hour before the planet transits in front of the star. So for this one, we have about an hour and a half before and an hour and a half after. So that leaves you with the planet transiting in the middle of those two times.
Okay. And so what's happening is the star is unobstructed for an hour and a half ahead of it, and then the
Correct.
planet starts moving onto the disk, starts obstructing it, and that lowers the light until a minimum, and then the disk of the planet is fully in front of the star. And then when the planet starts exiting, it comes back up to where it had been before.
Right.
And, so yeah, that's why it's symmetric, that dip. And
Yes,
Why it
they might
bounced
not
back.
all look symmetric from night to night. You might only get
Right.
30 minutes before, and then you might only have 2,000 seconds before, and maybe you have 2 hours after. So
right.
it's not always going to look this symmetric. This just happened to be one of the best ones where you got an hour and a half before and after.
Yep. And Wondergoon asks a question. I imagine it's easier to get a spectroscopic read on an exoplanet if it passes in front of its host star. Is that correct? And
Yes, we have not done any spectroscopic studies with our observatory yet, but I believe that is correct from what I know.
Yes. And it has to do with the fact that you can get a spectrum of the star without the planet, and then you get a spectrum of the star with the planet in front of it, and any differences must be due to are inferred to be because of the atmosphere of the planet. Because
Right.
if it's rocky or anything, of course, it's going to block the light completely. So if the spectrum changes, though, we assume it's because of the atmosphere of the planet, and we can get confirming data on that with another pass.
In fact, we've shown recently with JWST observations just that sort of thing, the
Just
spectrum,
that sort of thing.
and shown lines. Remember that was for technosignature lines, the fluorocarbon type of emission.
I was
line.
about to say, yeah, including one that supposedly is a techno signature, but I will go on record as saying that was a very poor detection.
Yeah, well, it's a low signal to noise, which means
Low
it needs a
signal
lot
to
more follow-up observation.
Right.
In fact, when
Right.
you're looking at different objects like this, you don't want to spend oodles of time observing. You want to do a quick and dirty sort of look to see if there's anything interesting. If there is, then you can come back and
Then
do a
you come back,
detailed follow-up to put the time and effort in to get a much better detection. And
It's like in Parker's case here, I'm going to sit here and say, you probably want lots of follow-ups on Trace 1B here, but you probably don't want as many on Qatar 4 because as dim as it is and as poor a signal to noise as you're going to get, spend your time imaging and working with what you can do best.
Well, the other effect, Parker, maybe you can say something, clarify this. When a planet starts covering the host star, we say that's an ingress, I guess, and an egress is when it leaves on the other side. So prior to when it undergoes both ingress and egress, so after egress, I guess, and then before ingress, doesn't some of the light from a host star reflect off the surface of the exoplanet itself? And that would increase the brightness that you see from the system. It's like there's an additional light source, right? Reflected starlight from the atmosphere, let's say, of a hot Jupiter.
And
that would,
I can answer that one. The answer is yes. It has been that effect has been detected, not with ground-based telescopes, though.
okay, so
I don't
because
know if it would be significant enough for our ground-based 20-inch telescope to detect, but
Right.
like Rob said, if you get a telescope out in space like James Webb, that's
you can-
definitely something that's feasible.
Yeah.
yeah, and that may give you another way of constraining both the composition of the surface of the exoplanet and its size relative to the host star.
In fact, they've gotten what's called a secondary eclipse already, where the planet goes behind the star.
Right.
And they've detected that brightening as the full reflective face of the planet has become visible. The starlight brightens a little bit, then it goes behind the star and it drops, and then it brightens as it comes out the other side before dropping back down to the normal again.
Right.
And they've done things with that as well, but that's a whole nother show.
So this would be what we would call a primary dip.
This is a primary eclipse. Yeah.
And the other one would be a very subtle, very hard to measure, probably not with this telescope, but who knows, secondary dip.
Yep.
Yeah, it wouldn't be measured, right? If you can't measure the reflecting on either side, then there's no way you could measure the change in brightness when the planet goes behind the star relative to us.
Right.
And you lose a little bit of light because
Just a
you're hiding
tiny
the
bit,
reflected
though.
light from the surface of that object.
Planets compared to stars just are not that big.
Yeah, so you're talking about like very small change in the normalized flux, right?
Right.
A fraction of a percent in that case.
Right.
That's it.
And I mean, this raises another question that's kind of interesting. What happens when a planet has a significant moon orbiting it? Should
And-
we see another minor dip onto the transit?
And the answer is we should. We haven't detected it yet, but we should.
We haven't, but as technology gets better, that's something to look forward to.
Absolutely.
Yeah, for sure.
And-
That's why, when you think about life around our planet, we at the beginning of the podcast, we mentioned, made a joke about the Borg. And that gives you a reason to think, well, you don't really want to tell other life forms that you're here, but you can't hide it.
You can't hide it.
Because we can detect planets going around other stars. Other life forms out there with the technology can detect planets going around our own sun,
Yep.
including our
Right.
planet. In fact, if they have advanced enough technology, they can use spectroscopy, as Wondergoon mentioned in the comments, to sample our atmosphere.
And know we're here.
And they'll know we're here. In fact, they'll know that there's life, as what you're alluding to,
Right.
is on this planet. And that may capture their attention and maybe come for a visit someday. Who knows?
Who knows?
Yeah.
I hope that they're not hostile if they do come for a visit, though, because they crossed interstellar space, and with all the challenges that entails, and got here. And as far as I'm concerned, I hope they think I'm a nice pet, because their technology is going to be so far beyond ours.
Leaps and bounds ahead of ours, yes.
Right.
Maybe we can, I don't know, give them COVID or something. Maybe that'll wipe them out.
There we go. War of the Worlds, right?
Exactly. Now, if any of you are interested in this type of topic, talking about planets and life elsewhere and so on, if you're interested in physics or science in general, one of the things you consider, though, is to come here to the University of North Dakota, where
Yes.
you can get involved in some of this stuff.
That's it. You can join and work with Parker and, Wayne here and all of us, and try to see what's going on.
Be famous
Be famous.
and rich at the same time. So, and the other thing we always do is we end with a quote from at the end of every podcast. But before we do that, I just want to thank Parker for joining us today. Thank you very much, Parker, for doing this.
Thank you, guys.
And we'll definitely have you on another time relatively soon so we can talk about the other stuff that
your
you're
other
involved in,
stuff.
your other
Yeah.
research, which is
Yeah.
what I did last summer, I guess, right?
Right?
So we have to have you on before the summer coming, because that will no longer apply, you see?
Right.
So we always leave you with a quote at the end of our podcast. Today, this quote is from Galileo. I only have to say one word. I don't have to give his first and last name. Everyone knows who it is. And we talked about Galileo today with the use of the telescope. And this quote is, "All truths are easy to understand once they are discovered. The point is to discover them."
Discover it.
Thank you very much for listening.
Y'all have a great week.